There is something sitting right next to every railroad track in the world, and almost nobody has ever thought to ask why it's there. You have seen it 1,000 times. Gray, jagged rocks, rough and irregular, packed between the wooden beams, spread across the ground on both sides of the rail. It looks like leftover gravel. It looks like someone dumped a pile of construction waste and just left it there. It looks, honestly, like the least interesting part of the whole picture. But here's the thing. Those rocks are not filler. They are not decorative. And the specific shape of those rocks, jagged, sharp-edged, broken, is not an accident. It is the entire point. And there is one more strange detail almost nobody knows. When fresh rocks are poured onto a track, trains are actually required to slow down until those rocks settle in. Not because the track is fragile, because the rocks are too new. That is the first clue that something much more interesting is going on here. The obvious guess when you first think about it is that the rocks are there to support the weight. A fully loaded freight train, 100 cars, millions of pounds, might need something under the track to keep it from sinking into the earth. And yes, that is part of it, but it is only a small part. Because here is the actual problem those rocks are solving. A train does not just push down, it pushes in every direction at once. When a train rolls over a section of track, it generates vertical force, yes, but also lateral thrust on every curve, and a forward force called track creep. A slow, grinding push that can cause the rails to inch along the ground over time, dragging the ties with them. At every rail joint, when a steel wheel hits the small gap between two sections of steel rail, the instantaneous impact can reach twice the static weight of the train. There is no rubber in this system, no cushion. Steel wheel on steel rail, transferring enormous force in a fraction of a second. The track needs to be rigid enough to hold its position, flexible enough not to shatter under shock, and it needs to drain water completely. Because if water collects under the track and the ground softens or freezes, the geometry slowly distorts and the rail starts to undulate. Early American railroad engineers, as late as the 1890s, noted that tracks built without any stone bed at all became genuinely dangerous at speed in winter. The ground, unprotected, would shift with every freeze. The track would follow it, so you need something under those rails that does all of this at once. Holds the track down, holds it sideways, absorbs shock, drains water, suppresses the weeds whose roots would loosen the ground, and can be repaired quickly when something goes wrong. And the answer that engineers arrived at, the answer still used across most of the world's railways today, is a bed of carefully selected, deliberately angular, freshly crushed stone. Here is where the shape becomes the story. If you used smooth river pebbles, the kind you see on a beach or a garden path, here is exactly what would happen. The moment a heavy train rolled over them, the smooth surfaces would slide against each other. The load would cause them to roll and shift. The track would move, the ties would migrate, and you would have a very expensive disaster very quickly. Smooth stones are like marbles. They do not grip, they flow. Crushed stone is different. When you break a rock, you create sharp, irregular faces, jagged edges, rough surfaces, unpredictable angles. And when you pack those angular pieces together under pressure, something remarkable happens. Each face catches the face of a neighboring stone. The edges interlock. The more weight you put on top, the more they grip each other. The whole mass transforms from a loose pile of fragments into something closer to a solid. A granular matrix that locks under compression and releases under none. This is the thing almost no one talks about when they look at railroad tracks. The rocks are not passively sitting there. They are actively gripping the track in place, and they grip harder every time a train rolls over. At the same time, the irregular shapes leave tiny gaps between every stone, and those gaps form a drainage network that carries rainwater down and away from the ties, keeping the ground underneath dry and stable. Angular stones drain. Smooth stones trap water. The standard ballast stone is between 1 and 3 inches. Small enough to pack tightly, large enough to leave those gaps. On high-speed lines that carry heavier loads, the layer of ballast can go down 20 inches deep below the ties. And underneath that, there is often a second, finer layer called sub-ballast, which prevents the fine soil of the ground from gradually mixing up into the stones and clogging the drainage channels. But the ballast does not stay perfect forever. Over years of use, the sharp edges of each stone get worn down by the constant vibration and weight cycling. As the edges round off, the interlocking weakens. Dirt and fine particles fill the gaps, blocking the drainage. The track starts to settle unevenly, creating small dips and bumps. Left long enough, those dips become safety problems. This is when the tamping machine arrives. It is one of the more remarkable pieces of machinery almost nobody has heard of. It moves slowly down the track on its own wheels, and at each tie it inserts a set of steel tines, long, thin tools, down into the ballast on either side. Then it vibrates those tines at high frequency, which causes the ballast stones to momentarily behave almost like a liquid, flowing and reshuffling around the tines. As the vibration stops, the tines squeeze together, forcing ballast underneath the tie, and the stones re-interlock in their new, tighter configuration. The track is lifted back to correct height. The matrix is reset. The machine moves to the next tie and does it again. One section of track, one night. Back in service by morning. Which brings us to that detail about fresh ballast and slow trains. When new sharp ballast is poured onto a track, the stones have not yet compacted. They sit in a loose, unset configuration. Their edges haven't found their neighbors yet. The matrix hasn't locked, so trains are required to run over those sections at reduced speed, not to protect the rails, but to give the ballast time to settle under repeated load cycles until the stones lock themselves into stable positions. The instability is expected. The slow traffic is the cure. The chaos is part of the engineering. And there is one more layer to this story: the name itself. The word ballast did not come from engineering. It came from the sea. Ships traveling empty needed heavy material in their holds to stay stable. Stones, mostly, taken on as weight at one port and dumped at the next. In northeast England, where ships came to load coal, they would arrive heavy with ballast stones and unload them at the docks before filling up with cargo. By 1704, those dumped stones were already being used on local coal tramways, the horse-drawn track systems that carried coal from the mines to the ships. The tramway builders needed something to hold the rails in place, and there was a free pile of stones right at the dock. Both the material and the name traveled from the sea to the railways and have been there ever since. There is a modern alternative: concrete slab track, where the rails are fixed directly to a rigid concrete base, does exist, and it is used on high-speed lines, inside tunnels, and on bridges. It requires almost no tamping, holds its geometry extremely well, and can last decades without major maintenance. But it costs roughly 28% more to build, and if a section of concrete slab cracks or shifts, the repair is slow, expensive, and usually requires closing the line entirely. There is no local fix. There is no tamping machine that can drive out and reset it overnight. Ballast's apparent weakness in that it moves, settles, and needs periodic attention is actually what makes it indispensable. A material that can absorb damage, then be reset, is far more forgiving than a material that holds rigidly until it doesn't. The rocks win because they move in a controlled way. Controlled movement is more durable than rigid perfection. Next time you drive past a railroad crossing, or wait at a platform, or look out a train window at the track running alongside, look at the rocks, not the rails, the rocks. Each one was quarried and crushed to a specific size, selected for its sharp edges, placed in a formation that locks tighter under every passing train, drains every rainstorm, and can be reset in a single night by a machine most people have never seen. The most overlooked material on the most overlooked infrastructure in the world, and it has been doing this quietly since sailors first tossed their stones ashore on the banks of the Tyne.